This is a discussion from section 3.6 of the classification of harmonic oscillators with damping. To begin with, in this case, we're dealing with a second-order differential equation that describes a harmonic oscillator with K as a spring constant, M as the mass, and B as the damping coefficient. And the solutions of this type of differential equation show behavior that shows three types of behaviors. But in this discussion, I want to remind you that M, of course, is a mass, always positive. K is a spring constant, of course, always positive. And B, the damping coefficient, is positive, but we also will consider the case when B equals 0, when there is no damping. The characteristic equation should look familiar to you at this point. And from this equation, we compute eigenvalues. This is a quadratic equation, so you're seeing the quadratic formula. There are three cases based upon what we see under the radical sign. If what we see, if b squared minus 4mk is a negative number, we're going to have two complex eigenvalues with a negative real part. The real part will be minus b over 2m, and if b is positive, this answer will be negative, and if b is 0, this will of course be 0. The origin in this case is a spiral sink. All solutions move towards the origin, but they spiral in. And the oscillator in this case is said to be underdamped because that spiraling indicates many repetitions of the mass moving past the equilibrium point, and then as it goes down, and then past the equilibrium point as it goes up. So it's said to be underdamped. Case 2, when the radicand, or the argument under the square root sign, is positive. In this case, we have two distinct real eigenvalues. They're negative because b is positive, and we'd have a negative in that situation. The origin is said to be a sink. All solutions move towards the origin. There are two straight line solutions that clearly move towards the origin, but all other solutions also move towards the origin without oscillating. So there are no oscillations, and in this case we say we're in a situation where we are overdamped. The third case earns the name of critically damped. Critically damped. Because this is a situation where the argument under the square root is 0. And in this case, we get one repeated negative real eigenvalue. The origin is still a sink. But this is a transitional state between two other situations, between case 1, where we have the spiral sink, and case 2, where we have no oscillations, and when we just have a classic sink. We will discuss in section 3.7 that we will argue that a bifurcation is happening as we move between the case of being critically damped, either into the situation where we have two negative eigenvalues and we have no oscillations, or into the case where we have two complex eigenvalues and we have an infinite number of oscillations. Okay, next slide, I'm going to show you three cases with equations. An example of our case 1, an underdamped example, is shown in our book on page 338, and this is our equation for our damped harmonic oscillator. Our M is a 1, our B is a 0.2, and our K is a 1.01. our eigenvalues end up being minus 0.1 plus or minus I. Using Euler's formula and saying that solutions are of the form e to the lambda t, we produce this complex expression, a complex function, I mean, and there is a real part and there is a imaginary part, and just as in the vector method of doing it, each one of these, the real part is a solution and the imaginary part is a real valued function. This is a real valued function that's also a solution. So our general solution is of this form, and because the real part is negative, means that we are going to be spiraling in towards the origin, and graphs of x and y also have to be oscillating, of course, as in this case sines, and this trigonometric functions combination, linear combination of sines and cosines. However, the effect of the e to the minus 0.1 t is to damp their amplitude, and the period in this case will of course be 2 pi. So let me just mention that the t in this case has to be 2 pi because there's nothing multiplied by the argument t, and that's the underdamped case. One more thing to mention too, as you look at this picture, we talk about this being oscillations. The horizontal axis, the y-axis, is our position, and if we just keep track of where the position is, so here is my initial condition, but that would correspond to a position here, and as we move to the left, we stop over here, and then we move back to here, and then back, and back, and back, and back, and our oscillations can be seen along the y-axis. We go from a positive value to a negative value, and we move from back again to this positive and back to this negative. Okay, thanks. In the second overdamped case, the point of looking at this example, so here's the example given in our book. We compute our eigenvalues, we get 2 negative distinct eigenvalues, and our solution would be written this way, our general solution. But more importantly, just looking at this, at 2 examples, should you start with an initial condition here, I want you to be clear that there is no oscillation going on. Yes, I'm crossing the y-axis, the v-axis. Y starts negatively, position is negative, and then turns positive, but then will only approach 0. We will not go back to a negative value for y, so there is no oscillation. Similarly, situation here, we start with some positive displacement, and although our velocity turns negative and stays negative as we approach the origin, we do not oscillate, we do not go past 0. So it's called overdamped. The third and final case is the critically damped example, and as I said, this is a transition between spiraling and just being a straight sink with an overdamped sink. And so in this case, this is an example of something that's critically damped because it has a repeated eigenvalue of -2. I actually jumped the gun here. I found an eigenvector, but I can't find an eigenvector from this system. I had to first have created the corresponding linear system, and with this as my eigenvalue, I went ahead and computed an eigenvector. This eigenvector v gives us the direction. This is a sink along this direction. All solutions, because lambda is equal to -2 solutions, all move towards the origin. And then let me remind you too that the dilemma of how do we decide how we are circling, we have 2 choices. If 1, 0 is our point of interest, one way I can come in, and this will turn out to be the correct way, is like this. But certainly a reasonable approach too would be to come in this direction and turn. So we're coming in from a direction similar to the red line, which is our eigen vector, and we approach the origin in the same direction. These are our two choices. The way we resolve it is we take our matrix 0, 1, minus 2 root 2, multiply it by 1, 0, and if the answer is going to be the blue line, at this point I expect to see a negative y value. If it's going to be the green line, I expect to see a positive y component. The x component ends up being 0, which actually makes sense as you look at the picture, but the y component ends up being a negative 2, which tells us that we are in fact, this is our correct curve, and I can then go on and draw the remaining curves. This is what my slope field would look like in this case. And you can see why this is a transition. We're trying to spiral, but this but the line of eigenvectors blocks the complete spiraling. But as we would transition into a case where we have complex eigenvalues, we'd see that we'd have a complete oscillating motion, and it would be called a spiral sink. Okay, thank you.